Alrighty, let's get started. So welcome everyone. Welcome to the workshop for an overview of machine learning algorithms. Also, I just want to point out that the computer vision workshop is going on at the same time, but I feel like this one really leads nicely into that one, so I would highly recommend afterwards for you guys to go check it out in the workbook. I think it's a nice more deep dive into like a specific machine learning algorithm, or not a specific algorithm, but a specific branch of machine learning. So yeah, I think it's an awesome follow-up. But anyway, so for this workshop, what hopefully we'll cover and what you guys will learn is what exactly machine learning is, the three main categories of machine learning, and I just want you guys to get a feel for some of the different algorithms out there and what they might be used for. So with that, let's jump right in. So what is machine learning? Machine learning is a subset or a subfield of artificial intelligence. So AI is kind of the overarching term for any kind of intelligent system, and then machine learning is just a branch off of that. So ML algorithms are all based in statistics and other mathematical optimization methods. An ML algorithm is usually trained using one of those statistical methods to then recognize patterns in your data. And so a trained algorithm can then be used to just be given a whole bunch of input data and hopefully give a good answer for either a prediction of a new value or a classification problem. And so there's tons of different algorithms out there. They all have their own unique applications and strengths and weaknesses. It really is a massive field. And just as a little example, in the top right there, I have a picture of Tesla's autopilot. So that's an example of like a classification problem where it's taking in all the pixels in the image, and you can see it's identified stop sign right here. Just based on the input features, which are all the different pixels, it's made that classification that this is a stop sign. And yeah. So types of learning. There are three main types of machine learning. The first being supervised learning, which is characterized by having labeled data, and you kind of correct the algorithm as you go. Unsupervised learning is characterized by unlabeled data, and it discovers the patterns in your data for you. So going into supervised learning, you already know what the correct output is and what you're looking for. With unsupervised learning, you don't really know what you're looking for. You just have a whole bunch of data, and your algorithm is going to find the patterns for you. And then there's reinforcement learning, which learns by doing, learns by interacting with its environment, and that one's a more continuous kind of cycle. So let's dive into those three. Supervised learning, as I said, is trained on labeled data, which is data with the correct output, whether it's a classification or just an output value. These algorithms are usually initialized randomly, although sometimes in certain cases you might choose the initialization for it. So more accurately, it's initialized in such a way that the outputs are going to be pretty much completely random. And then training it is going to be an iterative process. So you'll feed a supervised learning algorithm your input data. It'll go through, it will come up with its prediction. Then you'll go back, or obviously automate this, so it goes back, compares the prediction to the correct answer, and then uses that comparison to go back and adjust the model. And this keeps happening in the training loop over and over until after training, the model can just take those inputs and make hopefully accurate predictions. So once you have trained it, you'll no longer, you can give it data you don't have the output for, and it no longer will be checking the answer and adjusting itself. It just makes the prediction. So you can kind of think of this training process as something similar to quizzing yourself for a test. So you might have like flashcards, you read the question on the front, You think of your answer, you come up with your answer, you check your answer, and then based on if you got it right or wrong, you're going to adjust your knowledge of the topic and use that for the future questions you're quizzing yourself on, and then the final test. So some common supervised learning algorithms would include linear regression, which we have right here, logistic regression, which we have right here. And so linear and logistic regression are linear is trying to find the correlation between your input features and the output variable. And then logistic regression, you're just trying to split it into different categories, different classifications. You also have algorithms like k-nearest neighbors, support vector machines, and the back propagation algorithm for neural networks, and many more, but those are just a couple examples. Unsupervised learning, as I said, is trained on completely unlabeled data. So the same kind of data you might give for the testing of your supervised learning algorithm, you don't have the correct answer. So these techniques aim to discover the patterns in your data or to find descriptive models of the data. These algorithms vary a lot more in how they work. There's no kind of general process for how an unsupervised learning algorithm might work. They're all very different, but they may operate by learning like association rules. They may try to group data. They may be finding other patterns, just finding other patterns that provide you insight. And so some common algorithms for unsupervised learning include the a priori algorithm, k-means clustering, principal component analysis, singular value decomposition, and autoencoders. And if any of you have taken some more advanced linear data courses, you might recognize some of those terms. They're from a lot of those kinds of statistical analysis. All right, and our third kind of learning is reinforcement learning. So in reinforcement learning, you usually refer to the algorithm as an agent rather than a model, as you would in the other two. And so the agent learns by interacting with its environment. As it's either playing its game or doing what it's doing, it'll receive rewards and punishments for performing certain tasks or performing certain actions or reaching certain states. These algorithms will all learn continuously. So there's, unlike in supervised learning, where you have your distinct training phase, where you're doing that iterative process, and then you go and do the testing phase. With reinforcement learning, it's constantly learning as it's playing, and it never stops learning. So you can think of this one as really similar to teaching a dog to do tricks by giving it treats, right? So you say you're trying to teach your dog to sit, you say sit, maybe the dog doesn't sit the first time, it doesn't get a treat, eventually it does, you give it a treat, and now it will sit more readily in the future, and as it keeps doing that, it keeps reinforcing that behavior until it knows to do it on command. So with the reinforcement learning algorithm, it might receive its reward for, in the example I have here, this is OpenAI's hide and seek playing reinforcement learning demonstration. So they have, so the blue guys, right, they're the hiders, and the red guys are the seekers. So the blue guys, for every second or every frame of the game that they aren't being found, they're being rewarded. So they're going to keep trying to stay hidden. And the red guys, for every moment they are looking at the blue guys, they're going to be rewarded. So they're going to keep trying to do that. And as they reach those states, they're going to keep trying to stay in those states. And so reinforcement learning is especially useful in games and other kind of real-time contexts, because you know, in a lot of real-time contexts, right, you don't have the luxury of distinct phases, and same in games. There's no right answer per se. It's just learning by doing and by having good outcomes. So some common learning algorithms for reinforcement learning are Q-learning, SARSA, which is state action reward state action, and temporal difference. So machine learning is a very broad field. There are so many different specific divisions, subfields, and categories of machine learning. As an example, like just within QMind, we have different nodes for like computer vision, NLP, healthcare, generative algorithms, and so much more. As an example, I have at the top right here my project from last year, which was using computer vision computer vision for human attention detection, and then applying that to virtual assistant activation. So there's so many different things you can do with a machine learning algorithm. And then there's also a ton of overlap with other fields. Over the summer, I was at a conference and a NASA researcher was talking about how they were integrating reinforcement learning with automated planning, which is a non-machine learning subfield of AI. So one of the other branches of AI. And yeah, he was talking about how he was using the two to kind of better their algorithms to train the rovers to perform their tasks better on Mars. And so yeah, in general, there's just so much that can be done, so much that's yet to be done, and so many applications that are yet to be explored and discovered, which is honestly the premise of QMind innovation, and that's where we get to shine and discover these new applications. All right, so that's it for my presentation, but I do have a workbook I want to walk through with you guys. And if you want to follow along, it is in the GitHub. Hopefully you all have the link for it by now. And if along the demo you guys have any questions, just drop them in the chat. I'll keep an eye on it if you have any problems with setting it up. All right, so let me get that loaded up. Go. Keep doing. So I'll just give a little bit of time for anyone, or is there anyone who needs a bit of time to get set up before? Or if not, I can just jump right into walking you guys through what I have got here. Okay, I'll just jump into the demo then. Okay, so to start off, it's natural to kind of start with supervised learning. So the simplest supervised learning algorithm is linear regression. Linear regression, something you guys have probably all done before, especially if you've done like a math class, calculus in even high school. And so this is, the simplest kind of finding the correlation between your inputs and your output. So to get started, got to import all our libraries. This is how, for sure. Is that better? Awesome. Okay. So for this whole notebook, I'll be using sklearn to make these kind of simple models. sklearn, I think it's built on top of TensorFlow. It just makes it super easy to get working models going. They have like all the basic ones kind of built in. And then I also have one where I built out the whole thing so you can see how the inner workings actually work. All right, so start off by loading our data set. For our first example, I'm going to use sklearn's diabetes data set. All right, so we load the data and we'll take a look at what it kind of looks like. As you can see, it's very scattered, very all over the place. And I should mention, for the sake of this demo, I've just used only two features, only one feature and the output. So this is just a linear regression. All right, yeah. So we have our super scattered data. To build a model in sklearn, it's as simple as importing their linear model and telling it that you're making a linear model, model.fit, and there you go. It will fit a linear model to your data and let you know how it did. So, so here it's found its coefficient, which would just be the slope of the line in this case. And then we can make a prediction with just model.predict on our test data. And here I'll print out how it did. And so there we go. We can see that it's a very high error and that its fit is only about 0.5, which makes sense because our data is very scattered. There's not an incredible linear fit for it. But it's easy as that to do it. And then let's take a look at what it found. And this is only plotted on the testing data. And as you can see, it's done a fairly good job to just follow the general trend of the data. And then so using this to make more predictions, if you have more data you want to test, you just create your X test set, which in this case is just an array of numbers because we're only using two-dimensional. So you just give it your own list of numbers. You can replace that with whatever you would. And then tell it to make a prediction, and it would predict what the next value would be. So you do something there, and we would want to plot it. That. And oh, my bad. It does need to be two-dimensional. Okay, whatever. Scrap that for now. But you can give it your new data and make the prediction. Shouldn't be trying to do this on the fly. Okay, so next up is a perceptron. And so a perceptron is our kind of model of a single neuron in the brain. And this is what neural networks are built of. Neural networks are just a whole network of perceptrons, each firing into each other in a big network. But our single model is just we'll only be able to make linear classifications, and I've simplified it so that I can show you how the whole thing works from scratch, how the training algorithm works to make predictions with a model of a human neuron. So for this one, I'm going to use the iris data set, which is one of the most well-known and research data sets out there. Again, if you've taken a linear data class, you've probably come across it before. And then for this, I'm also going to make use of sklearn's train test split to split our data this time instead of doing it manually, to let it randomize the split so that we have random test data and a random training partition. So here, again, we'll just load our data. And here's how we called train test split to make that split for us. We just put our x's first, our two y's. It's always train, then test. And then you call it on the subset of data. So here, I'm only going to use two classes because, like I said, a single perceptron is only capable of doing linear classification. So it can only classify between two classes. You would need more perceptrons to make use of all three that are in this data set. And so just the first 100 are one class, or sorry, the first 50 are one class, and then the next 50 are another class. So we're capping it at 100. Our test size, we only want 20% of the data to go into the test set. The other 80% is training data. You always want most of your data to be training data. And then, yes, at a random state. So it's randomized. Okay, so here we'll plot the data, and I'm plotting it just with respect to the two features, sepal length and petal width. So as you can see, there is a very clear split between the classes, and our perceptron should be able to distinguish between the two. So we'll start off by defining an activation function for it. The activation function is the function that the perceptron will use to decide, based on the inputs, once they've all been multiplied by their weights, which I'll explain a little bit better in a second, to then decide with that final value whether it should be in class Setosa or versicolor. So here we're just going to use a simple step function. And so the step function just says if the activation it gets is greater than or equal to 0, then it's class 1. And if it's less than 0, it's class 0. There's no smoothing of that curve. It's just one or the other. All right, I'll come back to the predict function. And so we'll jump into how it's going to get trained. So it's going to take all of our X training data. And so here we're just going to grab the dimensions of the data. We see N is going to be the number of examples. So if the data was in like a big chart, right, this is just the number of rows. And then M, it would be the number of columns, the number of features we have, which in this case is 4, I believe. So we're going to initialize our weights. The weights are for each input feature, so each of M, in which case 2 of them would be sepal length and petal width. So for each feature, it's going to have a single value associated with it, the petal length, or the petal width, or the sepal length, and then it's going to multiply this value by the weight associated with that feature. Then inside, that's all going to get summed up. So all the features multiplied by all of their weights. And then, so that will give us 4 different values, and all those will get summed up, and that will be the activation. And so that happens in here. I'll come back to the epochs, but so for each X in X train, so for each input example, and for its associated proper class, for its associated label, we will start the activation at 0, and then we're going to group together each weight from the weights and each feature of the X. So we're going over each value in that one example. So yeah, we'll go over each feature, pairing the feature and its weight. We're going to add the weight times the feature value, and that will be our total activation here. But then we're going to add in a bias, and what the bias does is, if we come back to the fact that we're using a single perceptron, and it's a linear classifier, for this it would be the intercept. So this is if you have y equals mx plus b, this is the b, this is what's being added on. And so this allows it to classify like a little more advanced than just moving the line around. It also allows it to move it like up and down. So this is how we calculate our activation. And then we'll grab our prediction by calling the activation function. So here it's going to come up with a decimal number that's either going to be greater than 0 or less than 0. It's going to send it back up to here. And if it's greater than or equal to 0, it's going to be 1. If it's less than 0, it's going to be a 0. And so that gets our predicted class. Then the error is going to be calculated just as our y prediction minus the true label, which was paired up here in the loop. So from that, we use square error. Oh, it's moving. Sorry, I meant moving the linear function as in like the slope, right? So just like tilting that slope of it. And then the intercept lets you like physically move it, if that makes sense. Okay, awesome. All right, so we use square error so that we don't have any negative numbers. And then we add that to our total error. Then we can, now that we have what the error was, so this is the backpropagation algorithm. Sorry, I don't know if I mentioned that. So once we have our total error, we can go back and adjust the weights and the bias based on that. So I'll come back to learning rate here. You can ignore that for now, but essentially we're just going to take the weights and we're going to subtract whatever the error times the input was. And then the reason there's a 2 in here is because it's actually gradient descent is kind of what drives the backpropagation algorithm. And I don't want to go into like all the math behind that right now, but essentially when you get the derivative of the whole activation, or not the whole activation, the whole feed-forward algorithm, come back, you end up with the additional 2. You can omit it. You'll probably get the same results omitting it, but for the sake of correctness, I include it here. But essentially all we're doing is we're calculating how wrong it was for each of the examples, and then using that to go back and adjust all the weights based on how wrong each of those individual weights were. And then we do the same with the bias as well. And so that's going to run for every single training example we give it. And once it's done, it's going to come and save what the error was, calculate the accuracy of that iteration of the training cycle, as well as the test accuracy. So it's being trained on our X-trained data. And so we can test the accuracy of it on that, but then we also want to cross-validate with the testing data, which is stuff it wasn't just trained on, so we can see that it's not overfitting or overgeneralizing to just the training data we've been giving it. And so from that, we're going to save that and let us know how well we're doing, and I'll run this all in a second so you can see it all action. And I said I come back to talking about the epochs. So all the epochs is instead of only training on each training example once, right? We want to do this a bunch of times. So here I've just hard-coded in, we're only going to do it 10 times. But yeah, so it's going to train on all of our training data once, and then it's going to see how well it did, and then it's going to do it again, and it's going to do that 10 times. So that we can have a more well-trained model. So this is just defining all these functions, so we'll just run that. And now we're going to actually get these values. Like I said, like you will never have to code out like this whole thing. I just wanted to do this to show you guys how the actual inner workings of like a perceptron will work. In reality, like sklearn has a thing to build a perceptron in one line, just like we did with the linear regression up there. And then, yeah, there's all kinds of libraries and stuff for stronger customization if you go to something like TensorFlow or PyTorch. But anyway, so here we're going to get all our values from the training algorithm. It's going to use all the testing data we had above. And then we're going to plot how it did, as well as we'll get the outputs here as it trains. So let's see how it does. So as you can see, with this problem, because our data was so well separated, it was able to learn after one epoch. So it's only printing out the accuracy after it's tried every input example. In this case, because it's so well defined, the two classes, after looking at them all once, it was able to find something with 98% training accuracy and 100% accuracy on the testing data. And from there, it didn't really have anywhere to go, but we still wanted to train it a bit more. And it did have some error. As you can see, it got rid of that by the third epoch. But yeah, it's always great to overtrain your model rather than undertrain, as long as you're not overfitting to your test or your training data. And so here we can see that training curve just went straight up, and or the accuracy curve, as well as the final model. So this one, like I said, is a single perceptron. We have those 4 weights for each input feature and our bias, and so this is the linear model that it's come up with for our data. Okay, so now we're going to try it again, but with a little bit harder to separate classes. So instead of using the first two classes, the first two iris types, we're going to use the second and third because they're a little bit more vague, a little bit more overlap. So as you can see, there's some intermixing when plotted again with sepal length versus pet width. And so here we'll run that all again. We'll train it all again. Oh, sorry, I don't think I ever came back to learning rate. Essentially what learning rate does is you're slowing down the rate at which your model is learning. So in the case of the first one, the classes were so well defined that it didn't really change anything. It was still able to learn after the first epoch, but in general, you always want to apply a learning rate here so you don't overshoot the optimal weight values. If you let it just rectify the entire error times the input, it's very likely that your model is going to over-adjust itself and it's going to go too far in the right direction such that it becomes worse and it won't end up learning anything. It will just kind of oscillate back and forth between, way too high weight values, way too low weight values, and never hit on an optimal solution. So you do always need to include a learning rate when training a supervised learning algorithm. All right, so let's see how it does on this data. And so here we can see this time it was not able to do very well right off the bat. It only got 50% test accuracy, 51% training accuracy, tons of error. And then that's why we have multiple epochs, because it was able to keep adjusting here. It really did hit well by the second epoch, already 90% accuracy, still a bit of error though. And the biggest thing to note here is that although in the end, the final model did have considerably worse training accuracy and worse testing accuracy than previous epochs, it did reduce the error. And that is the goal of this particular training algorithm we used, backpropagation with gradient descent. It's not to maximize the accuracy, it's actually to reduce the error. And from that metric, it successfully did it. So when you're evaluating machine learning models, you always need to keep in mind, what is the most relevant metric here? Accuracy is a very common one, but it's not always the most important. Sometimes you want things like precision or recall, which are just other evaluations of how it handled the data. Accuracy is just the overall, like how many did I get right out of how many was I tested on. That's not always the most relevant metric to a problem. And it's also not usually what's being optimized for. Here it's mean squared error. And here's our training curves. So we can see this one fluctuated a lot more. As far as accuracy was concerned, it got really accurate, kind of flatlined, dipped down a ton, learned a bit more. But all meanwhile, although the accuracy was fluctuating, the mean squared error was generally going down. And so here's our final model for this one. All right, so now I will jump over. I see I'm running out of time, so I'll try to fly through this one a little bit faster. Unsupervised learning. So for this, like I said, these algorithms can get a lot more complicated, and they're all a lot more varied. There's not that general kind of pattern with them. So for the sake of this demo, I'm going to use k-means clustering, which essentially you have all of your data. What it's going to do is for each class you're trying to predict, it's going to create a centroid, which is kind of its center for the clusters. In this case, we're using an iris dataset again, but we're going to use all three classes this time. So it's going to come up with 3 centroids that it's going to kind of place randomly at first. And then it's going to try to minimize the variance within the clusters. So whatever's closest to the centroid, it's going to say it's in that class. and then it's going to calculate the total variance between all of the points it assigned to that class. And then it's going to move the centroids around to try to minimize that total variance for each class. So let's take a look at what I mean by all that. So first, let's look at the data. I plotted against the same axes again so for the sake of visualizing it. But as you can see, we have our three classes fairly distinct. Again, these two are a lot more intermixed. Yeah, there are fairly distinct clusters within it. So once again, we're just going to use sklearn's built-ins for this. They have realized k-means. It's as easy as calling k-means. We want three clusters and give it the random state, and then tell it to fit our data. Here, X is all of our training data. Important distinction is there is no difference between training and testing data for unsupervised learning because, like I said before, we don't have any labeled data. And so the algorithm's job is to find the patterns within the data for us, which means, yeah, it wouldn't make sense to give everything as testing data. There is nothing to train it on other than if you're going to kind of separate your data so that you have whatever you want to initialize your algorithm with and then apply it later on if you do, so you don't retrain it. But essentially, it's all unlabeled testing data. So here, we're going to use our k-means. So our k-means has been fit to the model in this line, and then we're going to use it to predict all of our data. And then the rest of this is just to kind of map it to the same classes that we see above. So the colors all match up, and we can compare the two classes and the classifications and its accuracy. So let's give it a run, and then I'm just going to plot here. All this is doing is all plotting the clusters that it found and then how it did. So as we can see, it was 89% accurate, and this is kind of what it's, this is our found cluster. So this is what it kind of classified everything as and decided on. And then here I've plotted the green is the ones that it got correct and the red it got wrong. So as you can see, it's kind of misplaced one of the clusters a little bit, but it's not a perfectly separable data set by the clusters. All right, so that's all I have for you guys. Reinforcement learning would take a lot more to get into. Don't really have the time for that, but I encourage you all to look more into any specific algorithms or any kind of branch that sparked your interest here. Like I said, I feel like this kind of feeds really well into the computer vision talk. So I encourage you all to go check out the workbook afterwards and see what was going on in there. Are there any questions before we head back? I think we have like a minute or two. We feature scales model. I think I did at the beginning. Actually, no, I didn't. No, I did no pre-processing anything on the data beforehand. Just put it all in raw. Thank you. So there are in the other talks, like every workshop has a notebook associated with it that you can always go in and see that the examples that we gave, as well as tomorrow during the hackathon, you'll have an opportunity to get your hands dirty and actually try out a machine learning problem yourself in a small group. And there, you'll have resources to ask questions and learn how to code your own machine learning algorithm from scratch.